In the world of large language models, reasoning is no longer just about generating answers. It's about how they get there. Traditional reinforcement learning methods rely on outcome rewards. Did the model get the final answer right? But that's like judging a chess player only by whether they won the game. What about the quality of their moves? The logic behind each decision. This is where process reward models, or PRMs, come in. They provide token-level feedback during reasoning, rewarding correct intermediate steps, even if the final answer is still wrong. This helps guide the model toward better reasoning paths, improves training efficiency, and reduces the risk of reward hacking. But here's the catch. Most existing PRM methods come with serious trade-offs. Some require expensive human annotations, step-by-step labels for every reasoning token. Others depend on Monte Carlo tree search to simulate expert behavior, which is slow and computationally heavy. And many online methods assume access to the expert policy or its reward function, assumptions that aren't always realistic. Even worse, some methods suffer from entropy collapse, where the model stops exploring, gets stuck in repetitive loops, and loses the ability to generate diverse, meaningful reasoning paths. So what if we could learn a powerful PRM without relying on human labels, without running MCTS, without assuming access to the expert's reward function, or even the expert policy itself? That's exactly what we introduce in our work, rePIRL, a novel framework that learns process reward models using inverse reinforcement learning, inspired by classical IRL, but adapted for the unique challenges of LLM reasoning. Let's break this down. At its core, rePIRL treats LLM reasoning as a token-level Markov decision process. Each step in the reasoning chain is a state. The next token is an action, and we want to recover a reward function that explains why the expert took those steps. Classical IRL solves this by learning a reward function from expert trajectories, without knowing the reward labels. But there's a problem. Estimating the partition function in IRL requires traversing all possible trajectories, which is intractable for LLMs with massive state and action spaces. So how do we scale it? We design a dual learning process. We train the policy and the PRM interchangeably. The reward model learns to assign high scores to expert trajectories. But instead of computing the intractable partition function, we use importance sampling. We sample trajectories from our current policy, not the ideal one. We then correct the gradient using importance weights. W equals \frac \x or \phi \tau, \pi \theta \tau. This allows us to estimate the gradient without ever needing to sample from the expert policy, because we don't even have access to it. And to avoid degenerate policies, we use maximum entropy reinforcement learning, a technique that encourages exploration by maximizing the entropy of the policy. This prevents collapse and keeps the model flexible. The result? A scalable, robust algorithm that learns PRMs from only expert trajectories, with minimal assumptions. But here's where it gets deeper. We don't just propose a new method, we unify the entire landscape of PRM learning. We show that existing approaches, like Prime, MathShepherd, MCTS, DPO, and DQO, can all be seen as special cases of our framework, each requiring additional assumptions. For example, Prime assumes that the outcome reward is the sum of per-step rewards, and that the reward can be written as r equals \log \frac \pi \theta \pi \textref. That's a strong assumption. MathShepherd uses MCTS to generate process rewards, but it's slow, and the rewards are noisy approximations of the final outcome. DPO skips reward modeling entirely, using preference labels instead, but it can't recover the reward function, limiting its use in downstream tasks. rePIRL, by contrast, makes the fewest assumptions. It's the most general, and therefore the most powerful. Now let's see how it performs. We evaluate rePIRL on 7 standard benchmarks, covering math and coding reasoning tasks like AIME, AMC, Minerva Math, LeetCode, and Live Code Bench. We use 2 base models, QN2, 5-3B Instruct, and QN3-4B Base. And the results? rePIRL outperforms all baselines, including state-of-the-art online and offline methods. On math reasoning, rePIRL achieves 33.5% accuracy with QN2, 5-3B, beating even the best outcome reward-only method by 2.8 percentage points. With QN3-4B, it reaches 41.6%, a 3.2-point gain over vanilla RLOO. In coding, it hits 27.7% on LeetCode and 39.8% on Live Code Bench, surpassing all competitors. But the real power of rePIRL isn't just in training, it's in what you can do with the trained PRM. First, test time training. We fix our rePIRL trained PRM and train a new policy from scratch, without any outcome rewards. The model learns purely from the process rewards, and it performs comparably to policies trained with verifiable outcome rewards. That means you can train reasoning models even when you don't have correct answers, just expert trajectories. Second, test time scaling. We use the PRM as a verifier to score multiple candidate responses. As we increase the number of rollouts, the PRM-based selector consistently outperforms majority voting, showing it can guide efficient, high-quality inference. Third, hard problem training. We train on a subset of extremely difficult problems, ones the base model fails on. Here, rePIRL shines. While outcome-based methods show no early progress, rePIRL delivers measurable gains from the start, converging faster and reaching higher accuracy. This proves that process rewards provide early, informative feedback, even when final answers are rare. We also test rePIRL without outcome rewards, just the PRM. And it still improves performance by over 13 percentage points on Math 500. This shows that our framework successfully recovers the latent reward structure of the expert policy. And we didn't stop there. We ran a full ablation study. We tested different base models, reward model architectures, RL algorithms, and rollout strategies. We found that using a smaller reward model hurts performance, but rePIRL still beats baselines. RLOO outperforms PPO and GRPO for process rewards. Including corrected policy trajectories, as pseudo-expert data dramatically improves stability and final performance. Importance sampling is crucial, just increasing policy updates doesn't cut it. Finally, let's talk about efficiency. rePIRL avoids training a separate value network, unlike many other methods. It only optimizes the policy and reward models. Training on QN2, 5-3B takes about 13.3 hours compared to 14.6 for Prime, making it not only more effective but also more efficient. And from an environmental perspective, by avoiding expensive MCTS and reducing reliance on human annotations, rePIRL lowers the carbon footprint of training advanced reasoning models. So what's next? We believe rePIRL opens the door to agentic reasoning, self-improving systems, and generalizable reward learning. Future work could explore combining rePIRL with intrinsic rewards, integrating curriculum learning, or scaling to larger models and complex multi-step tasks. In short, rePIRL isn't just a new method, it's a new paradigm. It shows that you don't need human labels, expert policies, or strong assumptions to learn high-quality process rewards. You just need expert trajectories and a smart way to learn from them. This is the future of LLM reasoning, not just getting the right answer but thinking the right way. And that's what rePIRL delivers. Thank you for watching. If you found this valuable, please like, subscribe, and share. For more deep technical insights into the latest AI research, stay tuned.